Assalamualaikum and hello everyone. Today we are going to present what we had learned from the Lab 2 session. The primary objective of this laboratory was to investigate 5mm operational amplifier. The first one is the inverting amplifier, non-inverting amplifier, integrator, differentiator, and summing amplifier by using LT-SPICE simulation. From this lab, we are able to understand the basic characteristic of this configuration, also able to compare theoretical calculation with the experimental simulation values. On the other hand, we are able to determine the effect of capacitor, bypass resistor, and internal operational amplifier offset voltage to the output voltage. For inverting, non-inverting, and summing amplifier, we examine that gain formula for both arrangement and deal with the output clipping issues that come up in the section on inverting amplifier. Besides, also verify the concept of virtual ground at the inverting terminal of summing amplifier.
The differentiator and integrator circuit, which are mathematical process that the ohm can execute. Besides, it also examine the function of the big feedback resistor in preventing DC drift and saturation for the integrator, while for differentiator's ability is to transform a triangle wave into a square wave output.
The inverting amplifier has Vin at inverting input terminal via resistor R1, while the non-inverting input is grounded. The voltage gain calculated as negative R2 over R1. From here, we can observe the clipping issue by using the R1 value is 1 kilo ohm, also R2 is 33 kilo ohm. As you can see here, Vin is applied directly to the non-inverting input with R1 is 1 kilo ohm and R2 is 10 kilo ohm. The voltage gain is calculated 1 plus R2 over R1, whereas the output signal is in phase with the input signal, which is high input impedance. Integrator amplifier use a capacitor in the feedback path instead of a resistor, so that the output is proportional to the time integrator of the input voltage. A square wave input is applied to the output. It is a shape of a triangular wave. The differentiator swaps the component of the integrator using a capacitor at the input and a resistor in the feedback path. The output voltage is proportional to the rate of change of the input voltage. Triangular wave input is applied. The output is a square wave. This is because the derivative of a constant slope is a constant value. The summing used a capacitor in the feedback path instead of a resistor at the input. The output is proportional to the time integral of the input voltage. When a square wave input is applied, the output is perfectly shaped triangular wave. This is because the integral of a constant is a ramp. The op-amp is constantly charging or discharging at the capacitor, that resulting in a linear.
For inverting, the voltage gain that has been calculated is negative 33 volt, while the Vout also the same. Meanwhile, for experiment result, we obtain negative 13.86 for 8 volt. For voltage gain, same goes to the value of Vout. Since the required output 33 volt far exceeded the power supply voltage, the op-amp was driven into the saturation region, causing the sine wave to be clipped at maximum possible output. The constraint in the op-amp's power supply rates which dictate the maximum undistorted output voltage. Non-inverting theory has been calculated 11 volt for voltage gain and Vout. Same goes to the experiment value. Negative feedback is used to tightly control the output. Due to the op-amp's high open loop gain, the feedback network forces the voltage difference between the two input terminals to be nearly zero. This configuration offers extremely high input impedance, which minimizes loading effect on the signal source. Vout for the integrator op-amp got negative 1 volt after has been calculated, while for the experiment value for Vout got 2.86 volt. The 10 mega ohm resistor is placed in parallel with the capacitor, specifically to address the instability which provide a DC pulse for the tiny currents and limit the DC gain to a manageable. There is a trade-off between DC stability and ideal integration when the resistor is added to guarantee the circuit is practically stable and operational throughout the time.
Differentiator Vout got -1 volt for theoretical part, while for experiment Vout got -5 volt. At high frequency, a tiny capacitor 100 picofarad is connected in parallel with the feedback resistor, function as a low-pass filter. By filtering out noise and avoiding the unlimited potential gain at high frequency, it restricts the high frequency gain, guarantee the circuit stability and usefulness. For summing op-amp, Vout theoretical value and the experiment value have the same value, which is -6 volt. If the input frequency is increased more than 300 Hz, the output amplitude may be decreased or the waveform may become distorted. For higher frequency application, a specialized op-amp with a much higher slew rate and gain bandwidth product must be selected in order to maintain signal integrity.
Inverting amplifier is clipping because the theory showed the output is -33 volt was too big for the 15 volt of power supply. Thus, the op-amp already hit the limit. Non-inverting ideal output show 11 volt where is well below the 15 volt supply limit. The op-amp stays in its linear region. There is no saturation or clipping issues, unlike the inverting amplifier. A capacitor and resistor is added for ideal integrator amplifies DC voltage infinitely. Every op-amp has a small, unwanted DC offset. This offset was continuously magnified until the circuit failed. By adding 10 megaohm bypass resistor in order to fix this DC drift and make the circuit become stable. Differentiator naturally amplifies high frequency. 100 picofarad capacitor is added to limit the high frequency gain. This made the circuit stable and able to ignore the noise. Summing amplifier can only change its output voltage so fast. The circuit should work fine at 3 kHz, which is too fast. The op-amp couldn't change its voltage fast enough to keep up, leading to the distortion. From this lab, we confirm the basic behavior of all 5 op-amp circuits for the ideal and real performance. Besides, we learned that real-world op-amp have strict limits that cause deviation from the ideal formulas. Last but not least, we also learned ideal circuit often fail in the real world. For instance, differentiator had to be modified with an extra capacitor to limit high frequency gain and ensure stability. This experiment taught us about valuable lesson about compromise in analog electronics. In order to ensure that the circuit is stable and useful, designing a successful circuit requires using fundamental concepts to overcome the limitation and defects of real-world components.